Okay, I just wanted to run through the simulations exercise we did. Um, so the first thing we did was just review some of what we had learned in the previous lesson. We learned that in Python, um, an expression is any representation of value, whether it's a number, a string, a combination of those, or a variable that contains one of those types of expressions. Um, So again, an assignment statement is when we say variable name equals, and then we give it whatever the value of that variable will be, whether it's a number or a string. And if it's a string, it must be enclosed in quotes. If it's a string enclosed in quotes, you cannot do any mathematical operations on it. So we have four different data types that we will be working with in Python. It changes a little bit when we get to pandas, but we have integers, we have floats, we have strings, and we have booleans. And booleans are expressions that, or variables that evaluate to either true or false. So the expression 5 is less than 7 is an expression that just evaluates to true. So if I just run 5 is less than 7, I just get the value true here, which you'll see in a minute when it runs. Um, you can determine the type of any expression by putting it into parentheses and then putting the word type in front of the parentheses. And let me just run to make sure we have everything loaded that we need here. Okay, so the new thing we introduced here was the idea of a list, which is a set of items enclosed by square brackets and separated by commas. So in this case, we have 6 individual strings, each one enclosed in quotes. And so in this case, each string is just a single letter. And we have a number of things that we can do with lists, which you can look at here when you get a chance to go back here. Okay, so then there's the idea of indexing a list, which is to say that everything in the list has an index number, and that number starts at 0 and goes up to 1 less than the length of the string. Okay, so this will all be for you to go back and look at and review. What we're going to do here is we're going to run through the tasks that you have. So in the first, you have to create a list called mylist that contains 4 letters and 4 integers. So something like this would work. And then you're going to print the 4th and 7th elements of that list, which means that you will print the values that have an index of 3 and an index of 6, because again, it starts at 0. So this first one prints the number 4, the second one prints the letter A, because those are the 4th and 7th elements of the list. Okay, then you're to create a variable with first name that contains your first name and last name that contains your last name. And so what we're actually going to do here is we're going to just give it a single string, and I'll put my name in here, and we'll do last name equals Rooney. Can use either single or double quotes. And then we printed it with this odd F string format where we have a print and then in the parentheses F followed by quote, and then anything that's inside the quotes will get printed, and then any expressions that are inside the squiggly brackets will be evaluated. So in this case, we said, okay, pull out from the string first name, pull out the item that has an index of 0, which would be the first letter in that string, or C, and then the same thing here, the first letter of last name, which is R, and then I just print my initials R. In this case, when we print it, it'll be my initials are CR. Okay, task 3 was we were to copy the code above, delete the hash mark, and replace every reference to Word with a reference to my list. So what we're doing here is we're saying my list is equal to, we're going to just take the hash mark, run this, and so my list has been created here, but we also created Word, and then we printed out every single letter and its index numbers. So now what we're going to do is we're going to go back to my list, and what we're going to do is we're going to replace running about anti-disestablishment with running about my list. And so what we see here is we go back to my list, and it pulls out every element: the A, the B, the C, the D, the 1, the 2, the 3, the 4, the 5, the true, the false, and then a list that's within a list. And so we find the index numbers for each of those. So A has two index numbers, 0 and 12, or negative 12. B has two index numbers, 1 and negative 11. And we do that all the way down. We do the 4 letters, the 5 numbers, and then we do the true and false. And then we see that the last element of the list is itself a list, but it also has index numbers and is treated just like anything else in the list. Okay, next thing we're doing is we're going to do a simulation. And what this does, this particular simulation will basically do the equivalent of rolling 2 dice 10,000 times and keeping track of the totals. And then it's going to put all those in a list, and then it's going to keep track of how many times we rolled: a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, 11, a 12. And then we're going to graph that using a histogram. And so that's what we see here. 7 is the most common, 2 and 12 the least common. And then what we're going to do in the next task is you're going to modify the code above so that it simulates rolling 3 dice. And so right here you can see we have a random number between 1 and 6. We have a second random number between 1 and 6. So all we're going to do is do a third random number, which would be the equivalent of adding a third die. So we'll do another rand.randint 1, 6. And now when we run this, we can see that instead of getting 2 through 12, we have 3 through 18. And we can see our histogram looks like this. So we could have done this with 4 dice or 5 dice, etc. And so this way we can simulate certain kinds of probabilistic events. Okay. Down here, what we're doing is we're saying, suppose that we have, let's say there's a survey and we wanted to find out, let's say we know that the population of Newton supports stricter gun control at a level of 57%. But we're going to take a sample to see if we can figure out what that true population proportion is. So we take a sample of size 2,000, but in this case, we're going to take it 100,000 times. And we're going to see what are the proportions of how many people in each sample are going to support gun control. And we'll simulate that by giving either a 1 or a 0. And we'll say if it's a 1, it means that you support gun control. If it's a 0, you don't. And so we run this. And so we're taking this, running this sample of 2,000, size 2,000, but we're running it 100,000 times. And what we find is that this is what we got. If the actual underlying real proportion is 0.57, and we were to sample that, we would get, and do it a lot of times, we would see that most of our samples are somewhere between about 0.562 and about 0.572. So we're pretty accurate in our sampling, and you can see that the lowest sample proportion we got was 0.543, and the highest was 0.597, and the mean of all the samples was 0.5703. So very close to digging out the true population proportion. And so obviously in most cases we're not going to know the true population proportion. We're just trying to figure that out by sampling. But what we can see here is that the idea is that most of our samples of any random sample are going to be somewhere around the actual mean or population proportion given the samples of sufficient size. Now, if we were to take a sample of size, let's say 100, and do the same thing again, you can see we get a much wider spread of possibilities here. And so that means that we have much less confidence in what we get from our sample because there's so much more variability. So the bigger the sample, the less variability we have here in all the samples of that size. And so the larger the sample, the more confidence that we can, with which we can speak about what we can infer from the sample, what we can infer about the population. Okay, so we changed it from 100, or from 2000 to 100. If we go up to 1000 or 1000, we'll see that we actually, oops, we went up to 10,000 by mistake here. Okay, now you can see that it's a very narrow range between 0.56 and 0.586. Now, at a certain point, you don't want your sample to be too much as a percentage of the population. There are also obviously logistical considerations. It's a lot more expensive to sample 10,000 people than 1,000. So frequently what's used is 1,500. And if we were to do that in this case, we would find that our samples are going to be between 0.54 and 0.60. And so that gives us a pretty good sense. Okay, 6 challenge is create a code that flips 5 coins 10,000 times and finds the distribution of the number of heads. And then there's a second challenge here, and those I'll let you try to figure out on your own. You can certainly submit this without those challenges done. Okay.